next step is to use the geodesic equation to derive the Euler equation. So the Euler equation is basically the three special components of the geodesic equation at first order approximation. Okay? So we start with the geodesic equation that we all know. So that's the covariant derivative along the direction u of the vector u, that's equal to 0. We now express u as a linear combination of its coefficients and the basis that we have chosen. We apply the product rule of derivatives to these product functions. Therefore, we are going to have e mu that we don't touch times the derivative of e mu, and now e mu not touched times the covariant derivative of e mu, which is this one. Then we start to turn on the brain, and we think, what is the covariant derivative of e mu? You say, this is a vector, therefore it should be the Christoffel symbol or the spin connection of that. No, because this is a scalar function. Why? Because e mu is outside the derivative. Okay? So if you look at this expression, that's the covariant derivative of a vector. This is a vector, and there you would have the spin connection and all this kind of stuff. But not on the u itself, because here is a covariant derivative applied to the coefficient only. There is not a basis. Therefore, this directional covariant derivative, now we go here, is actually just a standard directional derivative of a scalar function f, where f is u mu in this case. Then what we remind ourselves, that vectors are just directional derivatives. Therefore, this u nu times nu is just u intended as a vector, vector swallowing a scalar function, applied to a scalar function. Okay? Therefore, all of this part reduces to that. Okay? E mu that we are not touching, which is just left there. And then we have the covariant derivative along u, which is just a standard directional derivative along u, which is a vector. Okay? Therefore, this guy becomes that. The other part, we have the covariant derivative of the basis. The covariant derivative of the basis is expressed by the spin connection, because the spin connection tells us how the basis E is changing along the direction u. Okay? That's the very definition of the spin connection. Then what we have to do, once we have all our final expression made explicit in this way with the spin connection and the basis and the four velocities that we're considering, we just to fill up the ingredient with all what we found earlier. Okay? So now it's just a matter of plugging in stuff. And we do it for the ith component of the covariant, of the geodesic equation. We don't need a special component. Therefore, we are only focusing on the ith component. So now look at this expression, is exactly this one, except for the fact that we are not using the basis. Okay? Here you see an e nu and e mu, but keep in mind that these are dummy indices. You see, nu nu and mu mu. Therefore, I could as well relabel this one as nu and nu, such that I have e nu and e nu. Okay? So if we now look at this expression here, you see that if I do like that, I have exactly this expression. If I drop the basis, this one, then I'm left with the component only, with the if component only. Okay? Good. Now we need to fill up this stuff. So first we focus on this expression that I report here on the right hand side, where u is written in terms of a linear composition, a linear combination of the coefficients and the basis, as usually. Then I split this symmetry with respect to the time component and the spatial component. And then I just substitute all our ingredients that we had earlier with what we had up here. Okay, just plug in and substitution. That's what we get. Then I continue by plugging in also the four velocities with what we have here. And we arrive at this expression. Keep in mind that we always keep start at first order. Then we realize that we have VE and VE here. can group together such that what is left is going to be within the parentheses, and I realize the fact that this guy is actually the total time derivative of VE. Okay, so this is an operator, and it's the total time derivative with respect to the function to which it is applied. In this case, VE. Now that we have that, we can plug into here, and this will be this expression. We are left with this other term. Again, I have the symmetry with respect to mu's. Therefore, I split it in terms of a time component and the j component, where this one is going to drop, which is neglected because it's of second order. We are therefore left with the function that we derived earlier and to the survivor of the first part of the expression. And again, we make explicit now our spin connection component E0, which is this one. So we just plug it in, and you see this is the spin connection, working spin connection, working on U, working on U. And we're basically done, because then you see this is swallowed together with the 0th component that give us C up here. Okay, so we have this guy give us a factor of C, this is C, and together they give us a C to the power of 2. Basically, we are done. That's equal to 0, because that's the geodesic equation, and now we'll just get this guy on one side and this guy on the other side. Where, keep in mind, there is a change in the from big phi to small phi because of the definition of phi. Phi is defined as, sorry, the big phi is defined as phi over c squared. Okay, that's why you don't see the c squared here, because we changed the definition of phi. And we are done.